Hello and welcome back. Alright, now let's start building our convolutional neural network. So as usual, we define a class called CNN and we inherit from the nn.model. Alright, again we define our initialization function and we use the super function by Python to inherit the features of the nn.model. So we pass in the name of our class and our object self. Alright, and dots init open close. So now we inherited everything from nn.model. And now let's start building our neural network. So first of all, we go through self.cnn1, which is basically the first convolutional layer. So remember that we inherited from nn.model. That means we can use its all of its functions and attributes. So we use the conv2d method. All right. So conv2d is one of the nn.model methods that we inherited. So we go ahead and use it to build our first layer of our convolutional network. So nn.conv2d corresponding to convolutional 2d. Now we need to define first our input channels, and in that case our input channels is 1 because we have a grayscale image. Again, a grayscale image has one channel, alright? If you're working with an RGB or colored image, then you need to put 3 here. But since the MNIST dataset is the grayscale, that means the number of input channels of the image is 1. Okay? Now our output channels is how many feature maps we want. So this is arbitrary and I chose 8. So we're going to output 8 feature maps. Now the filter size is basically the kernel size. And we chose it as 3. Alright, so 3 means 3 by 3. So we just need to specify 3 and Python will understand that this is 3 by 3. Okay, so this is the filter size. Then we apply a stride of 1. Okay, so we're moving this window stride by 1 and we apply padding of 1. But this one you need to calculate, and this is how you calculate it here. So let's go through the calculation. So you want to have same padding. Alright, same padding means that your input size equals to your output size. Now the formula for same padding is basically your filter size minus 1 divided by 2. So in our case, our filter size is 3, minus 1 is 2, 2 divided by 2 equals to 1, and that's why we need to add a padding of 1 in order for the input to be the same size as the output. Okay, so same padding, input size equals output size. So again, I repeat, the parameters are input channels, the number of channels at your input, the number of feature maps, the filter size, the stride, and the padding. These are the parameters that you have to define for every conv2d layer. So let's calculate the output size now. Now the output size of each of the 8 feature maps, so remember that we have 8 feature maps and each of them, their size is this formula over here, which is going to be 28 as we said before, because we used the padding of 1. So the output should be basically the same as the input. But how did we get that? Let's calculate it using the formula. So it's our input size minus filter size plus 2 times the padding, all divided by the stride plus 1. So our input size is 28, our filter size is 3, and we use the padding of 1, so 2 times 1, divided by 1, our stride, plus 1. Okay, so that gives us 27 plus 1, which gives us 28, and 28, you should get back 28 because you use the same padding. Okay, so that's why you get 28. Now let's apply the techniques that we learned previously in the theory section to regularize our model. Okay, so we're going to perform batch normalization. Okay, batch normalization on the first layer. Now this is how you define it. We first define the we relate the batch norm to the object. Okay, so self.batch norm equals to, and this is how we do it. Again, you're inheriting from nn, so nn dot, and you can use their method of batch norm 2d, which corresponds to batch normalization 2d, and then you need to specify the number that the batch normalization is going to be performed on. So this number is basically nothing but the number of your output channels. Okay, so we need to perform it on 8 of the output channels. Then we go ahead and use our activation. So the activation we define as self.relu, and we again inherit from nn, so nn.relu. Then we go ahead and define our max pooling. This is our first max pooling. So again, nn.maxpool2d, and then we specify that the size of our pooling. In this case, we choose a kernel size of 2. Okay, so we're going to perform the pooling on a 2x2 window, meaning we're going to take 4 pixels and then perform max pooling, meaning find the maximum of each of these 4 pixels. Alright, now I've defined max pool 1, max pool 2. However, they're all the same size, okay, since they're all kernel size equals to 2. So you can just go ahead and define 1, and then we'll use it in the forward function. But you can also define 2. There's totally no problem. So this is the first part, okay? So we've defined convolution, batch normalization, activation using ReLU, and then max pooling. Now, after max pooling, the output size, of course, will shrink. Okay? So the output of each feature map is now nothing but the input size divided by 2, which is going to be 14. Because you're max pooling across a 2x2 window. So you divide by 2, and that gives you 14. Again, we define our next convolutional layer. This is the same exact thing, but this time our input channels is going to be 8. Because remember, our output channels from here is 8. Okay, and after we perform max pooling, each of these 8 output channels became of size 14. Okay, but we still have 8, so that's why our input channels is 8 now. So remember, don't confuse between the number of features and the size of the features. Okay, so the output channels is how many feature maps we want to output, and in this case we chose 32 feature maps to output. We chose then a filter size of 5, so as you can see we increased the filter size from 3 to 5. Then we chose a stride of 1, and this time the padding has to be 2 if we're going to use same padding. If you want to calculate it, okay, then you get 2. Okay, so you can just follow this formula and calculate it, and you'll get a padding of 2. So very simple. Filter size is 5. 5 minus 1 is 4. 4 divided by 2 is 2. That's why padding equals to 2. Now, output size of each of the 32 feature maps remains 14. Okay? So until now, there's no problem. Now we perform batch normalization on these 32 feature maps. So that's why I put 32 here. And we perform max pooling on each of these 32 feature maps. And then we get the size, which is 14 divided by 2. Since we're performing max pooling on a 2x2 window, so we get 7. Okay, so now each size of our feature map is 7 by 7, of course. Now we need to flatten the feature maps. So this is the part where we start building our feed-forward network, as we learned in the previous section, in the feed-forward network section. Okay, so we're done with convolution. Now it's time to jump to the feed-forward part. So we flatten the feature maps. We take all of our 7 feature maps, okay, and we flatten them. So we need to know the size of how many neurons to put, okay, because we're going to build that feed-forward network. So let's see. We have 32 feature maps, okay? Since here the last output was 32. So we have 32 feature maps, and each feature map is the size of 7 by 7, as we reached over here. So 32, and each of these 32 is 7 by 7. So in order to calculate how many neurons we need, means 32 number of feature maps times the size, which is 7 times 7. So 32 times 7 times 7 gives you 1568. That means our input features to our feed-forward network is 1568 neurons, and our output features, if we want to calculate it, then if you want to follow the formula, then 1568 plus 10 divided by 2, which gives you around, I guess, 700 something, 780 or something like that. So I just made 600. Now you can follow the formula input plus output divided by 2. So maybe that gives you 700 something. All right. Then you just put that whatever the answer you get. All right. You put it here. But I don't want to make it so complex. Okay. So I just put 600, and 600 should be fine because it's close to the 700 or 800, which is the one that we expected. And basically that formula I told you, which is the input plus the output divided by 2, this is just like a very traditional way of doing it. However, there's a lot of research and a lot of studies going on on how many hidden neurons to use for a specific type of problem. All right, so just in general, I told you that it's input plus output divided by 2. However, it's still arbitrary for you to choose. All right, but one main rule, remember, that the number of output neurons should be lesser than the number of input neurons. Okay, because basically if you think about it, then if the number of input neurons is the same as the number of output neurons, then your network isn't learning anything. It's just cheating. It's just copying from the inputs. So the number of hidden neurons, all right, should be less than the number of input neurons. Remember, this is the main rule. Okay, so we've defined our fully connected one, and now we're going to use another regularization technique, which is called dropout. Okay, so dropout, we explained it in the theory part, that it randomly disables some neurons, so that the neurons doesn't learn to all depend on each other. Okay, or to learn to fully depend on the data. Okay, that makes it much more robust. Okay, so self.dropout, we name it, and we again inherit from the nn. So nn.dropout, and we need to we need to give the probability of our dropout. So in this case, we want to disable half of the neurons in that layer, so 0.5. Then we go ahead and define our final layer. So self.fc2, fully connected to. Input features is nothing but the number of hidden neurons, so 600. Output features is nothing but the number of classes that you have, which in this case we're classifying 10 digits, so we have 10 classes or 10 output neurons. Okay. The forward function, very simple, just repeating the same concept. You first pass it through the first convolutional layer, pass your x, which is later going to be the images. Okay, then you pass it through the self.batchnorm1, okay, then relu, then max pool it, pass it through your CNN, batch norm, relu again, max pool again. Okay, all of these are defined here, and we're just saving. We'll just, first of all, we're inputting the images, saving it in the out, and then passing this out to the next layer, reassigning out, then passing this reassigned out here to the next one here, which is relu, reassigning it, passing it to the max pooling, reassigning it, passing it to the second CNN layer, reassigning it, and so on until you reach the end. Okay, now here is something you need to pay attention to. Remember that after max pooling, we need to switch to our feed forward network. That means we have to flatten the output. So this is where we apply the feed forward neural network as learned before. It will take the shape as, remember, batch size times 1568, which we defined over here. Okay, so the batch size is 100, so that means it's going to be on the shape of 100 times 1568. Therefore, we need to flatten it out, and this is where we flatten it. So we need to reshape that tensor. So out.view, okay, we make sure that it's 1568, okay, and then we leave it to PyTorch to figure out what's left here. But eventually, of course, it will be 100. Then we forward through our fully connected layer. So again, we pass it through our self.fc1, fully connected one, activate it using relu, then use dropout as we defined it here, and then finally pass it through the fully connected 2, and then after we get the final output, we return it. Okay, so that's defining the class, and let me run this, and there's no errors. So we're done with this part. Okay, in the next video we'll continue. So thank you very much.